Hi everyone, this is our final project video. The topic is detecting cancerous cells in gigapixel images. The first part of our video focuses on introducing the method we used and the results we got. The second part is the code. The first part contains the following subparts: introduction, data preparation, model training and evaluation, predicting and results, and limitation and future work. The goal of our project is to detect cancer in gigapixel pathological images automatically. However, there are some challenges. The medical images are hard to collect and has high resolution, hence its features are hard to learn. Also, the tumor pixels and normal pixels are imbalanced. We need a reasonable data preparation method. According to the paper, we could use patches instead of entire image as training data and use parallelized CNN model to process image from different zoom level. The dataset we use is WSI images from Cameroon 16. We use all 20 images provided by our professor as training images or test images. Sliding window is used to extract patches in both training and test dataset. We slide through the whole image, and for every 299 times 299 patches, we focus on finding tumor pixel in 128 times 128 central area. Since the scans of original image are huge and the predicting can be time-consuming, we use the coordinate of center to extract patches in level 3 to 6 as our input data. The specific process is as following. We first remove non-tissue pixels and get the coordinate list of center of every patches. For each center, we estimate whether it has tumor or not. We consider it as tumor patch if there is at least one tumor pixel in its central 128 times 128 area. Then we could get two lists, normal core and tumor core. We shuffle these two lists and cut out the longer list according to the length of the shorter list to balance the dataset. The model structure is shown on the slide. Here we use dense layer with 64 units as largest layer. In the training process, we use all images except 101, 110, and 91 as training images and use these three images as test images. We use the method mentioned above to prepare the training dataset and test dataset using for model evaluation. And we use transfer learning and input data to train the model. Then we save the weight for the following predicting phase. And here, we use accuracy, ROC, and confusion metrics got on the test dataset to evaluate the performance of the model. For test image 110, the test accuracy could achieve 0.87. These are the confusion metrics and ROC curve. For image 101, the test accuracy could achieve 0.89. And for the image 91, the test accuracy is 0.82. In predicting phase, we need to slide through the whole test image to extract patch and predict its label. We first need to load the model and pre-train weight, and then we predict and give a label for each extract patch. We generate the predict mask, and for the better results, we use the OpenCV to implement morphological transformations on predict mask. We then plot the processed predict mask and heat map and calculate the evaluation indicators according to the predict mask and ground truth. For the tumor 110, the predict mask, heat map, and the evaluation indicators are as followed. These are the results we got on the image 101. And these are the results we got on the image 91. The limitation for our project is the data isn't enough. Two of the slides contain over 2,000 tumors, however, the sum of number for all other slides is less than 2,000. This imbalanced data may bring bias to our model. Also, we use for inception v3 in our project and set the trainable as false, since we couldn't run trainable program when we set the trainable as true. When the slides in our project have significant difference from ImageNet, our model may not present the features accurately. Considering the improvement of our project, we can use more images and implement the data augmentation to get richer training dataset. Also, different models like MobileNet and DenseNet can be tracked if we could select the most suitable model for this task. The last point is that we consider a patch is a tumor patch if there is at least one tumor pixel in its central area. This may be the reason why the predicted patches are more than ground truth. We can do some adjustment in judgment method future.
Okay, let's talk about our code here. We have three files in our whole project. The first is the guess data. In this file, we prepare the training data for the following steps. And then we have the model file. In this file, we construct and train the multi-scale model and provide some metrics in the patches level. And finally, we have the prediction file. In this file, we detect the cancer cells through sliding window, draw heat map, and provide some metrics in the pixel level. First is about our guess data. In this file, the basic logic is the first we read an image into our memory, and we use sliding windows to walk through all the images. If we find one position is a tumor, then we add it into our positive dataset. To improve our balance between the positive and negative, we also add a negative if we found the positive. For example, for here we input a number is the 096, we get this image, and then we read this into our memory. We choose the 3, 4, 5, 6, 4 levels here. Finally, we get a dataset like this. First, we have the 97 positive samples, and also we need to add into the 97 negative samples. Thus, we have the 194 patches or samples. And for each sample, we have 4 levels. It's from the 3, 4, 5, 6. And finally, for each image, we have the same size. This is our training set, and then we can go to next step. Here we construct our model and make the training. The first step is to construct a good model. Here we use the 4 separate inception v3 here. And we choose the optimizer as Adam and choose the loss as binary cross entropy. After construct the structure of the model, we need to move into the training. In the training, the first step is we need to load all the data into our memory. And we start our training, we put the data into our model and get our result. One tricky method here is because we couldn't import all the images into our memory for one time, since we have limited memory. We use this just like the batches. For each time, we read some patches. After training a model, we save this model, and next step, we load this model and use other training. So in this method, we can train all the images here. And after get a good model, the next step is about test. In the test step, the first we considered is about accuracy. Here we choose the test index as 091. It means that we have this image, and we first need to know how accurate our patches are. And we can see the accuracy is about 78%. And then we also want to calculate the ROC curve and the confusion matrix. For the ROC curve, we use the scikit-learn package to complete this task. We can draw the curve here, and we also calculate the AUC here. And finally, for the confusion matrix, we use the pandas package to complete this. We can see this is a good confusion matrix, and this means our model is great. Then finally, we need to draw our final result and compare it to the ground truth. The logic here is first we need to load an image into our memory. Then we use a sliding window to walk through all the position of this image to extract all the possible patches in our images. This is just seems like our first step to getting data. And then for each patch, we need to predict the label of it. And finally, after get all the labels and all the positions, we can draw a heat map here. We can compare it into the ground truth. The first step here is also the load model. Because we have already defined the structure, here we only need to load the weight here. And then we make some prediction. As I said before, we have already extracted all the patches here. So for each patch, we need to predict a label. And now we can see that we complete all the prediction. After that, what we need to know is how to draw a heat map here. The method is first we start from a blank image. If we have a tumor, we draw this block as black. And then we have a mask as we define in the dataset. Also, we do some optimization here because we think that the tumor cells are less likely to appear only at 1 pixel and others around it will be negative. So in this way, we use a closing operation here. We also use the dilate here to eliminate noise and to expand the positive range. This can help us improve the IOU. This is the result of prediction and ground truth here. And we can draw this mask on the original file. We can compare the prediction with the ground truth. We can see that they are similar. And finally, we provide some numeric metrics in our implementation. We also use the pandas package here to calculate the confusion matrix. And after calculate all the results here, we can easily get the pixel level IOU, recall, and accuracy.